All right, well, greetings, you little apes hoodlums. So this will be your first lecture for energy. Just a heads up, this is going to cover three chapters, chapters 11, 12, and 13. So we'll be looking at kind of an exceptionally large assessment over this unit. Probably a 2-day or 1 day for multiple choice, 1 day for the FRQs, which involve a lot of math and stuff. But our primary focus here for the first couple lectures is going to be fossil fuels, which is chapter 11. Today's lecture, I promise to keep it to 15 minutes. I'm shooting for the sections covered on pages 233 through 243, although I may cut that short because I don't want to go longer than 15 minutes. All right? Anyhow, so when we talk about fossil fuels, what exactly are we talking about? You should know at this point that we are talking about coal, oil, and natural gas. All right? And you may be wondering, why do we call them fossil fuels in the first place? That's because they are essentially prehistoric organisms, but not dinosaurs, right? So we're not talking about compressed dinosaurs. We're talking about compressed plant or algae material from a really, really long time ago. Okay, but again, we're talking about coal, which comes from plants, oil and natural gas, which come from algae, and they form under slightly different conditions. We'll talk about that in a second. Now, this should also not be news to you guys. They are non-renewable resources, right? Which means they are created way too slowly for them to really replenish themselves. We're actually using them probably more than 1 million times faster than they could reform. And it's worth pointing out that the conditions that form fossil fuels in the first place probably don't really exist anymore. So when we talk about the formation of those fossil fuels, we're talking about back what they call the Carboniferous era. Really, it's kind of back in the Pennsylvanian and Mississippian areas here. Between about 300 and 360 million years ago, right in that era is when most of our coal, at least, was laid down. Conditions were mild, right? We had vast swamps. We actually had no ice on the planet at that time, or very little ice at least. And we had vast swamps, and dead plant material decayed really, really slowly in these swamp environments. Now, when fossil fuels form, over time, layers of sediment accumulated over dead plant material. So, particularly coal, we're talking about larger plants. Gooey plants like algae are what lead to oil and natural gas. But over time, these laid down at the bottom of these vast swamps. And bacteria, just at the time, hadn't really evolved to the point where it decomposed this material very quickly. And so that dead plant material was able to accumulate on the bottom of these swamps. Sediments accumulated on top of them, right? And in the case of coal, we're talking about heat, pressure, turning plant material into carbon-rich rock. So coal is essentially a mineral, it's a rock, or a precursor to a rock at least, right? So when we have coarse plant material, by coarse I'm talking about larger plants, buried under layers of sediment, heat, pressure, and time, and with time we're talking millions of years, kind of condensed that plant material into a really, really energy-rich rock that we call coal. Oil, we're talking about algae, which are kind of like microscopic plants. Same conditions, right? They settle to the bottom of the water. Sediment settled over the top of it. Heat, pressure, and time turn them into rich hydrocarbons, or oil, often referred to as petroleum. And natural gas forms in a very similar way to oil, although generally a little bit higher temperature to get natural gas. Now, pretty much every time you find oil, though, you also find deposits of natural gas alongside it. So, coal. Primarily what we're going to talk about in this lecture. It occurs in different grades based on variations in the heat and pressure during burial. So they kind of have different grades in terms of the quality of the coal itself. So those grades that we'll talk about are lignite, subbituminous, bituminous, and anthracite. Also worth pointing out that unlike oil and natural gas, in which case there's probably some pretty major discoveries yet to be made, all the coal that's available to us has pretty much been discovered. We don't think we're going to find really any major deposits of coal anywhere. Okay, but these are the 4 different grades, and they're separated in grades essentially by the quality, and they kind of have a different look. So you see the shinier type here, right? The real shiny, hard, denser coal is what we call anthracite. It's our higher quality, and this dull, kind of more brownish looking stuff is what we'd call lignite, which is our lowest quality coal. All right, and so notice we put peat in here. Peat is actually not a type of coal. It's kind of a precursor, right? But essentially look at the percentage that is fixed carbon, right? So we have a really, really high percent in our higher quality coal. Okay, bituminous is kind of our more common type that we have here in the U.S. at least, but it's not quite as high a quality as our anthracite. So lignite's our lowest quality. Anthracite is our highest quality, and then bituminous and subbituminous are kind of in between. But notice as we go down to greater depths, we get a higher quality coal. All right. So if we look at coal worldwide, the U.S. actually has a very, very healthy supply. We have about 25% of the world's coal supplies here in the U.S. But we'll notice that Asia and Oceania, that region has the highest percent. Okay, if we look at the available coal, again, the known coal deposits, and we're not likely to discover any major deposits, they could last us up to another 200 years or so at present rates of consumption, before it either gets too expensive to extract or too difficult. If rates, of course, increase, we're going to see that number go down over time. All right, so what exactly, first of all, are we using coal for? It used to be that coal was used for things as simple as heating a home in a coal furnace, and they even used to use coal to power steam engines for trains. As it turns out, we actually have better fuels for heating homes and better fuels for trains, etc. What coal is still widely used for, though, is electricity. Okay, coal, in the case of producing electricity, and this is something you definitely want to have down, by the way, coal is used to boil water. So we burn coal in a furnace, and we expose water, and that water boils. Boiling water, of course, as you know, creates steam, and we put steam under high pressure to spin a turbine, which is essentially a fancy word for a big paddle. And then a turbine spins a shaft in an electrical generator to produce electricity. And a generator is generally some sort of magnet, right, that spins inside some sort of chamber that's got a copper coil around it. So essentially we have a shaft connected to a magnet, right? So this would be our magnet right here, right? Here, outside of that, you're going to have your turbine, which again, like I said, is that big paddle, right? That spins, which spins this shaft, which spins this magnet inside a chamber where you've got a copper coil, and that causes electrons to move, which is electricity. Okay? This process, the steam generator, is the most common type of electricity generation. So whether it's nuclear power, natural gas, solar thermal, we're all using this sort of steam generation idea to produce electricity. Okay? That's why I said this process is something I want you to definitely have down. Efficiency, traditional plants, so our older coal plants, 65% of that initial energy is actually lost. Highly entropic process in our traditional coal plants. Only 35% of the energy in coal is actually converted to electricity, which, by the way, is more efficient than like a gasoline-powered engine in a car. Okay, our newer, more efficient designs, entropy is reduced. We get about 65% actually converted to electricity. So we almost double our efficiency with our newer coal plants. But still, we're losing a hefty amount of energy to heat loss. How do we go about getting our coal? So unlike oil and natural gas, coal is actually a mining process. We dig underground or at the surface to get at these massive coal seams. We have essentially two major types of mining. We've got surface mining, which you see over here, right? So if the coal is within 30 meters of the surface, we go in and we do the surface mining process and just dig down to the seams and then blast and dig our way through and remove that coal. All right. Subsurface mining, so our higher qualities, so like our some of our bituminous, but also our anthracite, which is much deeper. We tend to go subsurface mining. So if it's more than 30 meters deep, we dig shafts underground and then mine in that way. If you had to guess which type is probably more destructive to habitat, not talking what's more dangerous to the miner, what's more destructive to habitat would be our surface mining. All right. So with our surface mining, we have one of our major, aside from habitat loss, by the way, one of our major environmental impacts is acid mine drainage. We'll talk more about this when we get to our mineral resources unit later, but essentially you've got these tailings, which are leftover mine sediment, and they contain a lot of sulfur. Sulfur is kind of everywhere. And when water percolates through these sediments, it collects a lot of excess sulfur and creates sulfuric acid. Okay? Now, the acid itself is not a very strong acid. It's just that because it becomes more acidic, it is better able to dissolve some really nasty things like lead and arsenic, etc. Okay? And so when those things get out into our water, it creates havoc. Really, really nasty stuff for our fish and aquatic ecosystems. And because we get these large buildup of lead, arsenic, and cadmium, it makes it really difficult for plants to grow there, even after the mine is shut down. And then, of course, habitat is lost with surface mining as well. And aesthetic impacts can be huge, primarily with what they do a process called mountaintop removal. Okay? As shown in the next page here. So essentially what they do is, particularly in West Virginia, we have what these are called coal seams, right, that make up part of the mountainous West Virginia. They actually are literally removing mountaintops, scraping off these layers, filling in the valleys, and essentially, I mean, just for lack of better words, absolutely destroying the natural topography and habitat. That's what that mountaintop. So by far the most destructive way to get at our coal seams is this mountaintop removal process. All right. Now, as a result of some legislation in 1977, which is a great year, by the way, you'll have to guess why that's such a great year. But anyways, Surface Mining Control and Reclamation Act requires filling and reclaiming of surface mines after mining. It's a super expensive thing, but in the 70s we started implementing lots of environmental legislation. Okay, expensive process, but now it is required for coal companies who do surface mining to reclaim the surface mines to reduce acid mine drainage, and also prohibits coal mining in sensitive areas. So coal mining companies who do some of these destructive surface mining processes have to return the land essentially to a productive state again, which means taking measures to eliminate or at least reduce things like acid mine drainage and return things back somewhat to the natural topography. All right, some other issues of mining coal, and these things are nasty, what are called coal seam fires. And so underground in these coal seams, on occasion, a fire can start. So again, we're talking about things that are highly flammable, like coal. In the case of a spark or something like that, coal seam fires can start. And what's really kind of nasty and scary about these is once they start, it's essentially impossible to get them to stop. So they burn in a really low oxygen environment. And these seams, because they burn so slowly and there's so little oxygen, they tend to just kind of smolder over time. And there have been coal seam fires that started decades ago, like in Colorado, that are still slowly but surely smoldering away. And in that process, we're releasing some of the nasty things like carbon dioxide and mercury, right? And the ground collapses over time. So they've essentially had to abandon certain areas because of these coal seam fires. All right. Some other environmental impacts. Oh, there's the 15-minute mark. We will get to these next time. All right.